So we are now proceeding to our last slide, but we will call this video here as our new video for our next video in our slide. So we have specific heat, and the thing with specific heat is that we call it specific heat because different materials have different heat content there. There are some materials that can easily give off heat. There are those that can still hold the heat. What I have in mind is a frying pan, for example. Let me have a frying pan, for instance. If we have a frying pan and you you just use it just recently used the frying pan, you'll notice that after you use it, it's very hot, but it will not take very long for that frying pan to cool down. Maybe a few minutes after, if you happen to touch the frying pan, it will not be that hot, like the previous time you just get it out from the stove. So after you get it out from the stove, most likely that's the hottest time you can hold it, and then you can get burned, scalded, if you touch it right away. But try to observe. So that's a metal. The frying pan is a metal. Try to observe the boiled water. If you boil water and you put water after some minutes after, you set it apart, and then you let it wait for some few minutes. Let's say like 5 minutes after you just recently boiled it. Now you'll notice that after 5 minutes, if you hold the water there, you'll still get burned. So you'll observe that water cools down relatively slower compared to a metal. So a metal, after 5 minutes probably, would not be as hot as when it is taken from the oven. But a boiled water after 5 minutes may still be as hot as it is before. So uh, why does water don't cool down right away, compared to a metal? So again, it will be also about its ability to conduct heat, out or in. So we call that, we call the amount of heat that it can hold for so long a time as what we call a specific heat. Now, one thing about water, if you put water in a thermos, are you familiar with a thermos? So a thermos is a
Yes, sir.
container where you can stack up water, and even after a week, of stacking up water, you'll still observe water there to be still warm. And again, we observe that because of the very nature of water, that it can hold heat, for a longer period of time. Now, but not your frying pan. If you use your frying pan today, after 1 week, you'll notice that it will not be that warm anymore after a week, but water will still be warm. So again, because of the very nature of the material as well. Now, you will also observe that the shore, or the water, let's say you go into night swimming, in a beach. So we have there beachfront, shoreline, like in Boracay, for example. You happen to visit Boracay, you'll notice that uh, when evening starts to come, so after
Nè,
sun has set, you
nè,
know that,
nè.
excuse me, who's so again, you'll notice that after the sun sets, you'll observe that your uh, the sea there is still warm, even at night time. So why is it that the sea is still warm? Because of the specific heat of the ocean. So water tends to hold heat a little bit longer, no, compared to metals. No? And for our global warming, no, why is it that it's a serious issue? If the Earth is made up of three-fourths of body of water like an ocean, no, only one-fourth of the entire planet Earth, no, is land. So if most of it is water, and if the heat of the sun is always exposing this vast ocean, no, to energy, the energy contained in this ocean, no, will build up. So if the temperature of the environment, no, gets hotter and hotter, then the energy stored in the ocean is also getting, no, bigger and bigger. No? So why do we have more serious hurricanes this time around, no, compared to many years ago? They explain it because of the added energy that the oceans are receiving. No? So this energy will eventually turn into, no, some turbulence, no, in the atmosphere. No? Because this energy has to be used up. No? So if the energy in the ocean is much higher, no, because they can store more energy, no, like in the form of heat, then our hurricanes can probably, get stronger and stronger. So we notice that we have category 5 hurricanes, no, in just recent memory. You'll notice you have Yolanda, you have these many events in the US, no, that are category 5 hurricanes. No? So again, no, the thing about the nature of water, no? Water can store energy, no, for a longer period of time. No? So the quantity of heat absorbed by an object, no, is dependent on the kind of material the object is made of. No? So metals versus water, they can store different amounts of energy. No? So different objects have different capacities for storing internal energy. The internal energy of a substance is the total molecular kinetic energy, no, that is kept there. No? So again, no, when you consider the body of higher temperature, you call the energy there as internal energy. But once that energy goes out of the body, then we can now call that as heat. No? Here's an example. We have a Pyrex glass. No? So a Pyrex glass is usually placed in an oven. No? You can bake, no, your bread or your cake there, no? And it will not break. No? So what's the difference of a Pyrex glass to an ordinary glass? No? So a Pyrex glass can become hot easily, no? While water can remain cold. It takes a shorter period of time for the Pyrex glass to absorb heat and raise its temperature by a specified number of degrees. No? While it takes a large quantity of heat to raise the temperature of water by the same number of degrees. No? So it will take a long time to boil water, but also it will also take a long time to cool it down. No? Whereas your glass here, it is easily, no, heated, but also, no, it can also lose heat much easily. No? So that's the thing with Pyrex glass. No? So the specific heat, no, the quantity of heat required to increase the temperature of a mass of a substance by 1 degree Celsius higher. No? So there are listed specific heats of some substances, no? And you can always refer to that. No? Now we go to our last set of lesson for our chapter here. No? And we now go into calorimetry. No? So what is calorimetry again? It's a field of study where we measure, no, the heat that was present, no, or absorbed. No? So let's go to this one. So calorimetry is a science which involves itself of the measurement of the quantity of heat, transferred between bodies. No? So the device used, no, to measure heat is known as a calorimeter. No? So we can actually, determine the amount heat absorbed or given off, no, by one material. No? So but it's not the same as when you use a thermometer. No? A thermometer allows you to measure temperature directly, by putting it in a material. But a calorimeter, it does not have a gauge, or a scale that you can just look at, and say that this is the number of calories that the material contains. So the vast difference of measuring temperature and measuring, the amount of heat. So consider two bodies A and B, and they have temperatures T sub A and T sub B. So usually when we use capital letters T for temperature, we are dealing with, an absolute temperature. So our absolute temperature scales, we have a Kelvin and Rankine, while we have common Celsius scales, or common scales, I mean, temperature scales, we have Celsius and Fahrenheit. So Fahrenheit does not have uh, its temperature can become negative. Celsius also, you can have a negative temperature. But for absolute scales, the lowest temperature that you could have there is 0, and there's no value lower than that. And Kelvin is a kind of a measure that allows you to get a temperature, and the lowest temperature there is 0 Kelvin. Now, but for Celsius, 0 degrees Celsius is not yet the lowest temperature. You can still go negative. So we have a common scale for temperature, and we have an absolute scale for temperature. Two sets. Now, because B, is more massive than A. For example, you have a bigger body, B, and you have a smaller body, A. It is possible B possesses a larger amount of thermal energy. So if they have the same temperature, B will hold more heat. Now, if A and B are placed in contact, the flow of heat now will be from A to B. That is, if uh, if A is hotter than B, of course. The direction of the flow of heat depends on which body has a higher temperature, and not on which body has a greater amount of heat. So again, the heat flow is dependent upon the measurement of temperature. So the higher the temperature of one body, then the heat will flow from that body to the other. Heat is a quantity which we, when added to a body, raises the temperature of the body. And when removed, it will also decrease the temperature of the body. So specific heat is the amount of heat you need to raise the temperature of one body 1 degree Celsius higher, or 1 degree Kelvin higher, kung madugang mo nga amount of heat. Now, commonly, our specific heat is measured in calorie per gram per degree Celsius na unit. Now, one value of specific heat, guys, is common, is that of water, of course. Water, the specific heat of water, so if it's liquid, it has a different specific heat. So we usually indicate specific heat with letter C. And specific heat of water is one calorie every gram of water when you raise its temperature uh, 1 degree Celsius higher. So that's I so I just write C. So this is a Celsius scale. So let me draw a tiny circle at the top of. So that's per degree Celsius. Now when it is an ice, guys, so Is ice and water the same substances? Do you think the specific heat of ice, since they are of the same substances, are they the same in specific heat? Now we'll see here that the specific heat of ice, no, is only zero point 0.5 calorie. If you have 1 gram of ice, you will raise the temperature of ice, no, much more readily than when you, no, raise the temperature of a liquid water, no. Mas budlay initon ko, no, ang liquid water sa ice, no. You only need half a calorie of heat to increase the temperature of ice, no? But you need not twice the amount of heat if it's liquid water, no? So a liquid water is more, it will take time to add heat to it, no? Mas dugay siya. So again, no? Ice and water are the same substances except that one is liquid and the other one is solid, no? So these are the different phases of matter, no? Our phases of matter, we have solids, liquids, gases, and water can actually exist, no, in all these three phases all at the same time, no. You'll notice that when you have a block of ice, no, kung makakita ka mo sa isa ka block of ice, no, so if this is a block of ice and you notice that this is solid water, but at the top of it, no, there's liquid water also nga natunaw na. At the same time, makakita ka man da sang nagaasu nga parte, no. You can see some ano ni ng mist, no, dumiyara da nga do nagaaso nga part, no. So that's the converted water into, no, a gas, no. So the gaseous form of water is probably, you can call it as a steam, no. So water can actually exist in three different states, no, all at the same time, no. So there's the evaporated water, no, the ducted waters there that is coming out of the ice. At the same time, there's the liquid version, and then there's the solid version, no, all in one setting, no? So evaporation actually can happen at any temperature, no? But again, no, looking at the specific heat of these two materials, it will take a longer time to heat up water than to heat up an ice, no? So twice as much heat is needed, no, to heat up your uh, your liquid water, no? Okay, so that's the term we call as specific heat, no? Our heat capacity is the amount of heat required to change the temperature of the body, 1 degree Celsius higher. No? So they have some kind of a similarity, but our heat capacity, again, for different substances this time, they hold different amounts of heat. So again, when we talk about that pie earlier, that you just get out of the oven. Now, to know the flow of heat, guys, we have we have to have some kind of a mixture of hot materials and some cold materials. So if you have a container that has water in it, and you put ice into the bucket of water, so may balde kada filled with ice, and water. So we know that that bucket will be very cold. Well, at the same time, for example, you have a metal ball, so a metal ball that is placed, in a container. So you take this metal ball and you put it, in a certain bucket that is filled with water. So let's say this bucket is filled with water, and that water has ice in it, may mga ice cubes ni siya de. So this is very cold. This one is very hot. Now, if you put them together, then you now have a mixture, a hot metal and a cold container. Now, so what will happen? Which material will give off heat? And of course, no, if this is of higher temperature, no, so if you place this in a boiling water earlier, no, this metal ball. So we have a hot metal ball, and we have an ice cold water. No, so this is ice cold water. So of course, when you now dip it into this container, one material will eventually give off heat, no? And another material will absorb heat. No? So again, that's the thing we call as methods of mixture. No? So if two bodies of different temperatures are placed in a thermal contact, the amount of heat gained by the colder body is equal to the amount of heat given off by another body. No? Now, usually we use letter Q, no, to indicate, no, heat. No? So heat or the thermal energy is symbolized by Q. Now, there are materials who will eventually gain heat, no? And then there are materials who will eventually lose heat. No? So the heat lost and the heat gained by the other material should always be equal. No? This is according to this statement. No? So the heat given off by this hot metal, when you dip it here, will be the same amount of heat that is absorbed by this colder body. No? And you can have a sort of an equation. No? Now, usually, we write the equation of the heat, guys. No? Q. No? Q is usually, in terms of the mass of the body. Then we multiply the specific heat called C and the change in its temperature. No? I don't have a symbol for a triangle here. So we have there, no, change in the temperature. No? So let me just draw a triangle for you. So change in temperature is usually written down, no, as final temperature minus initial temperature. And we symbolize that with delta T. No? So delta T is the difference of the final minus the initial temperature. No? So eventually, no, when both of these materials are joined together, no, they will end up with a final temperature. No? But this one, its initial temperature is hotter, but when you mix it, no, its temperature will go lower. No? While the colder water, no, its initial temperature is cold, it will raise its temperature to a mixture temperature. No? And all of them will share the same temperature. No? So again, no, when we mix things together that is not of the same temperature, they will end up with a final temperature. No? But the delta T symbol there is equal to the final minus initial temperature. No? Now, a temperature of a metal specimen weighing 350 grams is raised to 100 degrees Celsius. It is then plunged into 500 grams of water at 20 degrees Celsius, no? Which is, no, in a 100-gram copper container. No? If the final temperature of the mixture is 25, no, determine the specific heat of the specimen. No? So the specific heat of copper, no, probably if you think of this as the copper material, the specific heat of copper is only 0.093 calorie per gram per degree Celsius. No? So this one will be the one who will give off heat, no? But its heat that it gives off will eventually be shared, no, by the container. So the container here could probably be called as your calorimeter container. This calorimeter container could either be aluminum or copper. No? So in this case, it's a copper calorimeter. Now, there's also water who will also receive the heat. No? So two materials will eventually, no, gain here. No? So the heat gain is the container and the cold water. No? So the one who will lose heat again is this metal ball. No? Now, I used earlier a symbol for heat as Q, no? But on some occasion they may also use letter H, no? To directly, no? Symbolize the heat there with that symbol H. No? So again, we can always equate the two. No? So that's the reason why it's measurable, because eventually heat, no, can be transferred. No? So you have there some sorts of an equation, but we can take up the solution for this, no, on some other time. No? Change of state. No? So you notice that when an ice is subjected to heat, you'll notice that it becomes liquid. No? So it changes from solid to liquid. No? So if you have a block of ice, if you subject this block of ice into heat, then you'll notice that it will become, no, liquid first. No? And then that liquid, when you still continue heating it, no, then it becomes a steam. No? So uh, the change of state of the water. So again, the different phases of matter, no? Phases of matter. So we have solids, no? Liquids, and gases. No? So uh, this is also, no, an effect of heat, no? When you subject, no, one material to higher and higher temperature. No? So if you add heat to a material, it starts solid, but it becomes liquid after a while and it turns into a gas. That's another effect aside from expansion. No? So when we talk about expansion earlier, no, that's also one effect of heat. No? So shrinking or expanding is another effect of heat. No? Now, similarly, no, the heat which is supplied to the block of ice, no, at melting point is used in changing its state, no, from solid to liquid. No? So if you put flame below this, no, so this will start to become liquid. No? Thus, during melting and boiling process, no, there is no change in temperature of the substance. No? So when water changes from solid to liquid, no, the state of that substance there, no, does not change its temperature. No? So not all increases in temperature is an indication of uh, heat transfer. So there's also heat transfer even though temperature may not actually change. No? And I think we call that as latent heat. No? Latent heat, no, is involved when the temperature does not increase, but the material eventually changes state. No? So again, latent heat. No? So latent heat, when you have a temperature that is the same. No? So at 0 degrees Celsius, we realize that water can exist in two states there, no? From solid into liquid. No? So the melting point and the melting point and the freezing point of water is both 0 degrees Celsius, no? Because although its temperature is the same, we notice that because the state changes from solid to liquid, that it is absorbing heat. No? But the heat that is absorbed there is called as latent heat. No? And for water, for substance water, so as it melts, no, it is absorbing 80 calories per gram. No? So we call this as the latent heat of fusion of ice. No? So once ice receives 80 calorie per gram at 0 degrees Celsius, then it will start to become liquid. No? Now for steam, I think that's around 540. No? So from boiling water to steam, no, at 100 degrees Celsius, you'll notice that it will need 540 calories per gram, no, to melt. No? So we call that as the latent heat of vaporization na naman. No? So at that temperature, 100 degrees Celsius, the temperature of the substance will not change until all of it now becomes steam, and the steam now will now go higher than 100. No? So the temperature of water will not go higher than 100 until such time that it is completely turned into steam. No? So when it is hot steam, then you can now increase its temperature. Now, ang liquid version of water, which is steam, no, can become superheated, no, and that's a time when you can increase its temperature to a much higher temperature, like uh 120 degrees Celsius, no. But before reaching that point, no, if there's still liquid there, then maybe no, you could not increase its temperature, no. A superheated steam has so many uses also, no. So you are given here, no, some equations, some problems probably, no, about no heat, and we'll take them up next time. So the mechanism of heat transfer. So for solid